Good afternoon, all. Myself, Dr. Abhishek Tiwari. Today, I am going to discuss GATE 2009 Metallurgical Engineering question paper. So, I will be discussing the next 23 questions. In my earlier lecture, I have discussed the first 22 questions of GATE 2019 Metallurgical Engineering question paper. So, question number 13 is the fastest diffusing element in iron at 1100 degrees centigrade is nickel, cobalt, chromium, and carbon. So, what is the answer? So, the correct answer is carbon. So, option D. And why this is so? It's because the atomic radius of carbon is about 67 picometer, and that of nickel is 149 picometer, and our atomic radius of cobalt is 152 picometer, and atomic radius of iron is 156 picometer, and atomic radius of chromium is about 166 picometer. So the interstitial solid solution form when the solute atom is small enough, radii up to 57% of the radii of parent metal atom. So to fit at interstitial sites between the solvent atoms, and for substitutional solid solutions. So these are the state solutions that form when solute atoms replace solvent atoms, and this type of solid solutions forms only if solute atoms are large enough to replace the solvent atoms in the lattice. Moreover, the atomic size of solute is nearly similar to size of solvent atoms. So here, radius of carbon is smaller than iron. Therefore, it will form interstitial solid solution. So it will be diffusing very fast compared to other metals, because for nickel, cobalt, iron, and chromium, their atomic radius is similar. And if we look at the phase diagrams of these, then as the iron cools further to 1394 degrees centigrade, its crystal structure changes to FCC, crystalline structure, and in this form it is called gamma iron or austenite iron. So at 1100 degrees centigrade, the iron will be in the form of gamma iron, and gamma iron can dissolve considerably more carbon, as much as 2.14% by mass, at around 11 at around 1147 degrees centigrade, and this gamma form of carbon saturation is exhibited in stainless steel. So these are the phase diagrams, corresponding phase diagrams. So this is the FENI phase diagram. This is CO. This is FECO phase diagram, and this is FECR phase diagram, and this is FECR phase diagram. So at around 1100 degrees centigrade, this gamma has around 2% of carbon solubility. Here we cannot infer what solubility will be of nickel and cobalt and chromium. Chromium we can see at 1100. We can see this is the solubility, but actually we have to look at the fastest diffusing rate. That will be in case of carbon, because of the difference in the atomic radii of carbon and iron. Question number 14. Hydrogen bonds are stronger than ionic bonds, metallic bonds, van der Waals. bonds and covalent bonds. So what is the correct answer? Though, so the correct sequence of strength of bond is metallic bond is greater than ionic bond is greater than covalent covalent bond greater than hydrogen bond greater than van der Waals bond. So the correct answer is C. So hydrogen bonds are stronger than van der Waals bonds. Question number 15. The carbide that is primarily responsible for intergranular corrosion in austenitic stainless steel is. So we have to choose between Cr23, C6, Fe3C, SiC, and Mn3C. So the normal alloying composition of common austenitic stainless steel is 18% chromium and 8% nickel and 0.06% of carbon. So during reheating at 600 to 850 degrees centigrade, carbon, which is highly mobile, diffuse to grain boundaries. As we are increasing the temperature, it will diffuse to the grain boundaries. And a lot of chromium, which is less mobile, diffuse only from areas neighboring grain boundaries to react with carbon and form chromium carbide. So at high temperature, chromium will react with carbon and form Cr23C6 at grain boundaries. Okay, so the grain boundary in grain boundary area Cr23C6 precipitates will be there. An extensive carbide precipitation at grain boundary results in corresponding chromium depletion in neighboring areas. Thus, the chromium content may go below 12% in area neighboring grain boundaries. When chromium is below 12%, passivation cannot occur and this area becomes susceptible to localized corrosion. It is also called sensitization of austenitic stainless steel. So the sensitized structure, which is area neighboring grain boundaries, suffers intergranular attack when exposed to chloride environment and mechanism is as explained in this figure due to small anode at grain boundaries compared to grain size and also large area of inability of passivation. So the correct answer is Cr23C6. So the answer option is A. During low strain rate less than 0.1 per second, deformation of a metal at room temperature. The one that deforms by twinning mode is Fe, Mg, Al, Ni. So we have to choose out of these four metals. At room temperature, Fe has BCC structure, Mg has HCP structure, aluminum has FCC structure, and nickel has FCC structure. Of these three common crystalline structures, BCC, FCC, and SCP, the SCP structure is most likely to form deformation twins when strained because they rarely have a sufficient number of slip systems for an arbitrary shape change. High strain rates, low stacking fault energy, and low temperature facilitate deformation twinning. Primary mechanism of accommodating plastic strain at low temperatures to crystalline metals are twinning and dislocation slip. Twinning and slip are competitive mechanisms for crystal deformation. Each mechanism is dominant in certain crystal system and under certain conditions. In FCC metals, slip is almost always dominant because stress required is far less than twinning stress. Compared to slip, twinning produces a deformation pattern that is more heterogeneous in nature, and this deformation produces a local gradient across the material and near intersection between twins and grain boundaries. The deformation gradient can lead to fracture along the boundaries, particularly in BCC transition metals at low temperature. So the correct answer here is Mg, because Mg has SCP structure and SCP structure favor twinning. Question number 17. In a tensile creep test of a metal, Nabarro hearing herring mechanism is favored over Coble mechanism for option A, larger grain size and lower temperature; option B, smaller grain size and higher temperature; option C, larger grain size and higher temperature; option D, smaller grain size and lower temperature. So first we need to understand what is creep. So creep is plastic deformation of materials at elevated temperatures, which is time dependent, requires stress required elevated temperature, that is greater than zero point 0.4 times melting point on absolute temperature scale, is a life limiting factor for several critical high temperature components. So the creep has three stages: primary, secondary, and tertiary. Primary or transient creep region. So they are continuously decreasing creep rate. You can see in this the creep rate, that is d epsilon by dt, is continuously, the slope is decreasing with time. Indicates the creep resistance, that is strain hardening. So that means that strain rate is decreasing. That means it is strain hardening. And the secondary reason is secondary creep regime is a steady state creep region, and creep rate d epsilon by dt is constant with time in this region, and the plot takes almost a linear shape, and the region should be as long as possible. That means it should have longest duration. So the constancy of creep rate is attributed to balance between strain hardening and recovery. Recovery is a softening process, and this regime determines the peak life of a high temperature component, and this regime regions should be as long as possible. Now, strain hardening. I'm taking this topic in detail. So, strain hardening in ductile materials become harder when plastically deformed as a result of extensive generation of dislocations and straining in crystalline structure, and also called work hardening or cold working. And recovery, stored strain energy is removed by virtue of dislocation motion and enhanced atomic diffusion at elevated temperatures, resulting in annihilation. Annihilation means dislocation, positive dislocation and negative dislocation, they vanish off. So vanishing of dislocations and improved ductility. And depending on the temperature and stress, different deformation mechanisms are activated, though there are generally many deformation mechanisms active at all times. Usually one mechanism is dominant, accounting for almost all deformation. So various mechanisms are bulk diffusion, that is Nabarro herring creep, Second is grain boundary diffusion, that is also called oval creep. Third is glide controlled dislocation creep. So dislocation move via glide and climb, and the speed of glide is dominant factor on strain rate. Fourth is combined controlled, sorry, climbed, sorry, climb controlled dislocation creep. So dislocations move via glide and climb, and the speed of climb is dominant factor on strain rate. And fifth one is Harper-Down creep, a low stress creep mechanism in some pure materials. So basically, at low temperature and low stress, creep is essentially non-existent. So as we see in the stress strain curve, at low temperature and low stress, the deformation is elastic, and at low temperature and high stress, material experience plastic deformation. As also we can see this thing in stress strain curve. But at high temperature and low stress, diffusional creep tend to be dominant, while at high temperature and high stress, dislocation creep tend to be dominant. So this is the Navarro hearing creep mechanism. So in Navarro hearing creep is a mode of deformation of crystalline materials and amorphous materials that occurs at low stresses and held at elevated temperatures in fine-grained materials. In Navarro hearing creep, atoms diffuse through the crystal. So atoms diffuse through the bulk of the grain. So and the creep rate varies inversely with the square of grain size. So fine grained materials creep faster than coarse grained ones. And Navarro herring creep is solely controlled by diffusional mass transport. And this type of creep results from diffusion of vacancies from regions of high chemical potential at grain boundaries subjected to normal tensile stress to regions of lower chemical potential where average tensile stresses across the grain boundaries are zero. So you can see here that the stress is in this direction. So the atoms diffuse from here to here, and vacancy is diffused from here to here. So this is the Navarro hearing creep. So the diffusion takes place in the grain inside the grain, and it is not along the grain boundaries. Now I will discuss Koval creep. So in Koval creep is a form of diffusion creep and is a mechanism for deformation of crystalline solids. Contrasted with other diffusional creep mechanism, Koval creep is similar to Navarro herring creep in that it is dominant at lower stress levels and higher temperatures than creep mechanisms utilizing dislocation glide. Koval creep occurs through diffusion of atoms in a material along grain boundaries, and this mechanism is observed in polycrystals or along the surface in a single crystal, which produces a net flow of material and a sliding of grain boundaries. So here the diffusion occurs along the grain boundary. You can see atom and vacancy diffusion happening along the grain boundaries, and this is the applied stress. So Navarro herring creep does not have a dependence on grain boundary thickness and has a weaker dependence on grain size. In Navarro herring creep, the strain rate is proportional to 1 upon d square as opposed to 1 upon d cube dependence for Koval creep. Lower temperature favor Koval creep and higher temperature favor Navarro herring creep because the activation energy for vacancy diffusion within the lattice is typically larger than that along grain boundaries, and thus lattice diffusion slows down relative to grain boundary diffusion with decreasing temperature. So Navarro hearing creep occurs at high temperature and low stress and small grain size, and Powell creep occurs also at low stress and fine grain size and temperature. So temperature is less than those for Navarro hearing creep, and the grain size in Powell creep is much finer because when we have finer grain size, then we have more grain boundary area, and more grain boundary area will favor uh, Powell creep because the diffusion occurs along the grain boundary, uh, while whereas in case of Navarro herring creep, the diffusion occurs inside the grain, inside the bulk structure of the grain. So actually, if the grain size is slightly bigger than the bulk diffusion will be happening. So grain boundary area will be less. So in Navarro herring creep, slightly more in size compared to Cobalt tree. So the correct answer is C. So Navarro hearing creep mechanism is favored over Powell creep mechanism for larger grain size and higher temperature. Now, question number 18. Beach marks are commonly observed on fractured surfaces of metals after a answer is fatigue test. So these are the beach marks. You can see these circular kind of lines. So these are the beach marks, and this is the ductile fracture. This is from this reference. So beach marks are concentric rings in a fatigue region which resemble tide marks on a beach, and crack advancements are caused by changes in environment and load. Whenever there is an interruption in propagation of a fatigue fracture, a unique feature of macroscopically visible marks or ridges may be found. Beach marks must not be confused with striations, although they frequently are present on the same fracture surface. There may be many thousands of microscopic striations between each pair of macroscopic beach marks, and beach marks do not occur if part has been operated continuously or with only brief interruptions in service. The most obvious difference between striations and beach marks is size. Striations are extremely small ridges visible only with an electron microscope, and beach marks are much larger than striations. If they are present, they are normally visible to unaided eyes. The other difference between striations and beach marks, as previously mentioned, is factors that cause them. Striations represent the advance of crack front by one load application in many ductile metals, whereas beach marks locate the position of crack front when repetitive fluctuating load was stopped for a period of time. Question number 19. The length of internal cracks in two samples of same glass is measured to be C1 is equal to 0.5 millimeter and C2 is equal to 2 millimeter. The ratio sigma 1 upon sigma 2 of fracture strength of two samples is. So here we are talking about glass. So Griffith theory of brittle fracture because glass is brittle. So here we have a formula sigma c is equal to 2 E gamma upon pi c, where E is Young's modulus, gamma is surface energy, and C is the crack size. So if it is internal crack inside the metal, then it inside the glass. So this crack size 2c is the length of this oval structure, and if it is at the surface, then it is the crack size is c. Okay, so when it is internal, then we have to take the size of the flaw divided by 2 for calculating c. So sigma 1 divided by sigma 2 will be equal to under root of C2 upon C1, that will be equal to 2 upon 0.5 will be equal to 2, where sigma C is the critical value of stress required for propagation of flaw of length 2c, and E is Young's modulus, and gamma is the surface energy per unit area of the material, and S2c is the crack length. So the correct answer here is 2, that is option C. Question number 20. Two blocks of same metals are to be welded, and the configuration that will undergo the least distortion after welding is. So in this actually, when we have this double V groove, so the double V groove with the less angle, one is with the larger angle, another with smaller angle, so with less angle will have the least distortion after welding. The most suitable the question number 21, most suitable non-destructive method for detecting small internal flaws in a dense bulk material is dye penetrant method, ultrasonic inspection, eddy current testing, and magnetic particle inspection. So first we need to understand what are these methods. So dye penetrant method or liquid penetrate inspection (LPI) is a low-cost inspection method used to check surface breaking defects in all non-porous materials such as metals, plastics, or ceramics. The penetrant may be applied to all non-ferrous materials and ferrous materials, although for ferrous components, magnetic particle inspection is often used instead for its subsurface detection capability. LPI is used to detect casting and forging and welding surface defects such as hairline cracks, surface porosity, leaks in new products, and petty cracks or in surface components. DPI or dye penetrant method is based on capillary action where low surface tension fluid penetrate into clean and dry surface breaking discontinuous is penetrant may be applied to the test component by dipping, spraying, or brushing after adequate penetration time has been allowed. The excess penetrant is removed and the developer is applied. The developer helps to draw penetrant out of the flaw so that an invisible indication becomes visible to the inspector, and inspection is performed under ultraviolet or white light depending upon the type of dye used, fluorescent or non-fluorescent visible. And second is ultrasonic testing is a family of non-destructive testing technique based on propagation of ultrasonic waves in object or material tested. In most common ultrasonic testing applications, very short ultrasonic pulse waves with center frequencies ranging from 0 0.1 to 15 megahertz and occasionally up to 50 hertz are transmitted into the material to detect internal flaws or to characterize materials. Eddy current testing, also commonly known as ECT, is one of many electromagnetic testing methods used in non-destructive testing. NDT making use of electromagnetic induction to detect and characterize surface and subsurface flaws in conductive materials. Fourth is magnetic particle inspection is a NDT process for detecting surface and shallow subsurface discontinuities in ferromagnetic materials such as iron, nickel, cobalt, and some of their alloys. And the process puts a magnetic field into the part, and to identify a leak, ferrous particles, either dry or in wet suspension, are applied to a part, and these are attracted to an area of flux leakage and form what is known as an indication, which is evaluated to determine its nature, cause, and course of action, if any. So the correct answer is ultrasonic inspection because it is used to detect small internal flaws in dense bulk material. Question number 22. Allegating is a defect commonly observed in rolling. So these are the four rolling defects: wavy edge like this, and the edge cracks. So we have cracks at the edges and the zipper cracks in the center of flat rolling and allegating like this. So the form sheet will adhere to rolled surface and to follow the path of their respective rows. So the upper portion of the sheet will be like sticking to the upper roll and the lower portion of the sheet will stick to lower roll. So actually it will split and process is this defect is called alligating. So the correct answer is D, rolling. Question number 23. The standard deviation rounded off to one decimal place of the following set of five numbers is 68899. So we arrange in increasing order of numbers. So 68899. So the mean for these five numbers is the sum of these numbers divided by 5 will be equal to 40 divided by 5 will be equal to 8, and median is calculated by n plus 1 by 2 number, that is third number is equal to 8. So sigma standard deviation is equal to under root of 1 upon n minus 1 sigma of xi minus mu square from I varying from 1 to n. So this will be equal to 1.224. So the correct answer is 1.224. Question number 24. A FCC crystal with the latest parameter of 0.3615 nanometer is used to measure the wavelength of monochromatic X-rays. The Bragg angle theta for reflection from 111 plane is 21.68 degree. The wavelength of X-rays in nanometer rounded off to three decimal places is. So we know the Bragg law 2d sin theta is equal to n lambda, where n is a positive integer and lambda is the wavelength of the incident wave, and d is the interplanar distance. D is equal to a upon under root of h square plus k square plus l square. So 2 into d is a upon under root of h square plus k square plus l square. So this will be equal to 0.3615 nanometer divided by under root of HKL is 111. So 1 square plus 1 square plus 1 square sine theta. Theta Bragg angle is given 21.68. So sine 21.68 into 1 into lambda. So we can calculate lambda to be 0.1542 nanometer. Next question. A plate of width 100 centimeter and thickness 5 centimeter is rolled to a thickness of 3 centimeter. If the entry velocity is 10 centimeter per second, the exit velocity of the plate in centimeter per second is. Assume no change in width of the plate. So we have to conserve the volume. So volume before volume at the time of entry and volume at the time of exit will be equal. So H0, W0, L0 will be equal to HF, WF, LF. So H is the height, W is the width, and L is the length. So if we divide both sides with the time, so H0, W0, V0 is equal to HF, WF, VF. So where V0 is the entry velocity at the entry, and this is the velocity at the exit. So width has not changed. So W0 and WF will cancel out. So VF will be equal to V0 H0 upon HF. So VF will be equal to 10 into 5 by 3 will be equal to 16.67 centimeter per second. Question number 26. Match the reactors refining sites in column 1 with the corresponding refining processes. So here the blast furnace runner will match to external desilkinization, because in this blast furnace scenario, this you can see in the flow diagram that it happens at the blast furnace scenario, so desilkinization. So P is 4, and AOD, that is argon oxygen decarburization. So uh, Q corresponds to 1, and decarburization, and torpedo car. So here in torpedo car, here it is external desulphization. Here is written dephosphorization, but dephosphorization and desulphization both occur actually. So we are talking about actually external desulphization. I'll discuss in later slide and later. So one should not confuse with this. So in torpedo car, uh, external desulphurization occurs, and in BOF, basic oxygen furnace, dephosphorization occurs. So these are the correct option is A. So I will explain these processes also. Desulfonization is conducted as a pre-treatment process by adding iron oxide such as mill scale and sintered ore fines to hot metal in runners in cast house of blast furnace or in transfer vessel. AOD, argon oxygen decarburization, is a process primarily used in stainless steel making and other high-grade alloys with oxidizing elements such as chromium and aluminum, and after initial melting the metal is then transferred to an AOD vessel, and where it will be subjected to three steps of refining, decarburization, reduction, and desulfurization. Hot metal desulfurization takes place in a torpedo car that transport the hot metal from blast furnace to steel plant, and typical reagents are calcium carbide, soda ash, and blends of magnesium and lime. During the torpedo desulfurization, the reagent is injected into the hot metal via a lance, and nitrogen is utilized as a carrier gas, and the reagent reacts with sulfur in the hot metal and sulfide CaS and Na2S ascend to the slag layer, and this slag is then dragged off with a skimmer. In integrated steel plants, removal of phosphorus normally takes place during primary steel making process, usually BOF process. In order to meet new demands for phosphorus control, it is necessary to improve understanding on thermodynamics and kinetics of phosphorus partitioning reaction between slag and metal melts during steel making process. Dephosphorization of steel has become a very important metallurgical technique in steel making process to produce high quality steels, as phosphorus content is controlled by reactions in BOF, and double slag technique has generally been applied to obtain low phosphorus killed steel. Now question number 27. Match the injection metallurgy technique in column 1 with corresponding objectives in column 2nd. So aluminum wire feeding correspond to deoxidation, calcium treatment correspond to inclusion modification, and argon ringing corresponds to mixing of liquid steel, and lime powder injection corresponds to desulfurization. So aluminum wire feeding corresponds to deoxidation. So P is 4, and calcium treatment corresponds to inclusion modification. So Q is 1. So the correct option is D. So I will explain this also. Aluminium is used for deoxidizing and grain refining in steels. It is a stronger deoxidizer. It is also used as nitrate former and as an alloying element. Its ability to scavenge nitrogen from steel makes it a useful addition in drawing quality steels, especially for automotive applications. Aluminum may be added to steel making, furnace steam, ladle, ladle furnace, continuous casting, tundis, or ingot mold. Each type of addition has its specific purpose, and each addition produces its own characteristic results. Aluminum is very powerful deoxidizer, but has a disadvantage because because of its low density and density of liquid aluminum at steel making temperature 1300 1600 degrees centigrade is about 2 tons per cubic meter, while the density of steel is at this temperature is greater than 7 tons per cubic meter. Therefore, when aluminum is added to liquid steel bath, it floats at steel slag interface where it quickly gets oxidized. Hence, relatively small amounts of aluminum actually make contact with the steel. Therefore, we use wires of aluminum because where we can mix it properly. So wire feeding helps in overcoming this advantage since it is a force feeding of aluminum deep into the steel bath. Calcium treatment is done to transform oxide and sulfide inclusions in the steel to less harmful inclusions, which can have beneficial effects on properties. When calcium is added to steel, it can modify alumina inclusions to calcium aluminate or react with sulfur to form CAS. The argon ringing of liquid steel is carried out for obtaining homogeneous temperature, composition, and promotion of slag metal refining reaction. The argon ringing of liquid steel is reported to be an excellent process for flotation and separation of non-metallic inclusions. Lime is the cheapest hot metal desulfurizing reagent which is being used. So lime powder injection is used in desulfurization. Now, next question. The table providing the correct option, correct information about crystal structure, coordination number, and packing fraction. So, crystal, we have to determine the coordination number and packing factor for each crystal structure. So, first we deal with FCC. So, atomic factor is equal to volume of an atom volume of atoms, total number of atoms in a unit cell divided by volume of unit cell. So this will be equal to number of atoms per unit cell multiplied volume of each atom divided by volume of unit cell. So this will be equal to 4 into volume of number of effective atoms in the FCC is 4. So 4 into 4 by 3 pi r cube divided by a cube. So 4 into 4 by 3 pi r cube divided by this 4r will be equal to a root 2. So a will be equal to 4r upon root 2. So q will be, so this will come out to be 0.74, and the phase center atom touches neighboring corner atom. So the coordination number is 12. Now atomic factor for BCC, atomic packing factor will be equal to volume of atoms in a unit cell divided by volume of unit cell. So number of atoms per unit cell in BCC is 2 because 1 in center and 8 into 1 by 8 for corner atoms. So 2 into 4 by 3 pi r cube divided by a cube. So this will be equal to, sorry. So this is 4r will be equal to a root 3. So this will be equal to just 1 second. So this is 2. So The correct answer is 0.68. So the packing factor for BCC is 0.68 and the coordination number for BCC structure is 8 as any atom in the unit cell has 8 atoms at its nearest as its nearest neighbor. So atom at the body center is touching 8 corner atoms. So the coordination number is 8. Now the diamond cubic structure. So in this actually this is a variation of FCC structure. So this is FCC plus there are 4 atoms in the tetrahedral weights. So the atomic factor for diamond cubic. So will be equal to number of atoms per unit cell multiplied by volume of each atom divided by volume of unit cell. So this will be equal to four are the four atoms inside this at tetrahedral sites. So 4 plus and 6 at the face center. So 6 into 1 by 2 plus 8 corner atoms. So 8 into 1 by 8. So this will be equal to 8 number of atoms, effective atoms into 4 by 3 pi r cube divided by 8. We have a root 3 will be equal to 8r. So this is calculating like from the diagram we can calculate it. So A will be equal to 8r upon root 3. So 8 into 4 by 3 pi into divided by 8 by root 3 q. So this comes out to be pi root 3 upon 16. So this packing factor for diamond cubic is 0.34 and the coordination number for diamond cubic structure is 4 because this atom is connected to 4. So 4 nearest neighbors. So unit cell has 4 atoms as its nearest neighbor. So coordination number is 4. So the correct answer is A. Okay, yeah, this correct answer. Now question number 29. So this is a very straightforward number. So match the phase transformation in column 1 with the second. So paritactic has reaction liquid plus alpha giving you beta, and monotactic is liquid giving you liquid plus beta, and eutectoid giving you gamma giving you alpha plus beta, and syntactic reaction is liquid one liquid 1 plus liquid 2 giving you alpha plus beta. So so correct answer is A. Question number 30. In a typical SEM, the information about topography and atomic contrast are obtained from secondary electron and backscatter electron respectively. So the correct answer is C. Match the ceramics in column 1 with column second. So mullet is 3Al2O3 dot 2 SiO2, or it can be represented as 2Al2O3 dot SiO2. So this is used in refractories, and spinel ferrite is Ab2O4 is used as a soft magnet, and tungsten carbide, as you know, it is very hard material, so it's used as a cutting tool, and barium titanate BaTiO3 it's used as a piezoelectric detector. So the correct answer is D. Question number 32. An aluminum single crystal is loaded in tension along 1 bar 0 axis. Among the following slip systems, the one that will be activated first is, so the slip system will be activated when Schmidt factor is not 0. So the Schmidt factor has to be calculated for each system. So Schmidt factor M is equal to cos phi into cos lambda. So you calculate the angle between this and this, and the angle between tensile axis and glide direction. So you can calculate cos phi and cos lambda. So this comes out, limit factor for option A comes out to be 1 by root 6, not equal to 0. So therefore, slip system A will be activated first. For other options, it will be 0. So the answer will be, the semi factor will be 0. So it will not be counted. Now, question number 33, the correct Moore circle construction for the stress state given below. So we have been giving sigma x is equal to minus 10 megapascal and sigma y to be 30 megapascal and tau xy is given 20 megapascal. So we know the principal stress sigma 1 comma 2, that is sigma max and sigma min, is equal to sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 by square plus tau xy square. So tau max will be equal to, and tau max is that is the maximum shear stress is under root of sigma x minus sigma y whole square plus tau xy whole square, and tan 2 theta p, that is the angle at which the principal or normal stresses are there. So will be equal to tan 2 theta p will be equal to 2 tau xy upon sigma x minus sigma y. So sigma 1, 2 we can calculate. So 10 plus 20 under root 2, and sigma 2 is 10 minus 20 root 2, and r is tau max, that is equal to 20 under root 2, and the center is sigma x plus sigma y by 2 is equal to 10. So center in B option it is at 10, center is at 10, and this is sigma 1, that is 10 plus 20 root 2, so that will be around roughly 38 point something, and here it will be around this will be around minus 18. So option B is the correct. Match the automobile components in column 1 with the corresponding manufacturing processes in column 2nd. So engine block generally is made of by casting process, or also sometimes by cast iron, because to dampen the vibrations, and brake bed is uh, made using powder metallurgy because it requires high friction strength. So, and the connecting rod is made using forging, and the door panel are made by sheet metal forming. So the option is B. And question number 35. So the equilibrium constant for the following reaction at 300 Kelvin is carbon graphite plus 2H2 giving you CH4. So delta H is given, delta S is given, and R is given. So delta G is equal to delta H minus T delta S. So this comes out to be 50 minus 50,900 joule per mole, and delta G is equal to minus RT ln K. So we equate this, and we put the value of R and T, and we get A is equal to 7.3 into 10 is to 8. So the correct answer is T. So thank you for your attention.